first part of ISRO VSSC Technical Assistant previous year question paper with a detailed solution. The exam held on 2021. The total equivalent capacitance of the series parallel combination of capacitors across A and B shown in figure is answer option A 4 microfarad. Here C7 equal to 12 microfarad, C6 equal to 12 microfarad and C8 equal to 12 microfarad are in series. Therefore, C equivalent 1 equal to value of equal capacitor divided by number of capacitors. Therefore, we get 12 by 3 equal to 4 microfarad. C equivalent 1 equal to 4 microfarad is in parallel with the C6 equal to 8 microfarad. Therefore, C equivalent 2 equal to 4 plus 8 which is equal to 12 microfarad. C4 equal to 12 microfarad, C5 equal to 12 microfarad are in parallel with the C equivalent 2 equal to 12 microfarad. Therefore, C equivalent 3 equal to 12 by 3 which is equal to 4 microfarad. C equivalent 3 equal to 4 microfarad is in parallel with the C3 equal to 8 microfarad. Therefore, C equivalent 4 equal to 4 plus 8 equal to 12 microfarad. C1 equal to 12 microfarad, C2 equal to 12 microfarad and C equivalent 4 equal to 12 microfarad are in series. Therefore, total C equivalent across A and B equal to 4 microfarad. Question number 2. The figure shows a 3-stage amplifier each having voltage gain as indicated. Find the total gain. Answer is option D 126 dB. We know that 2 or more amplifier circuits can be cascaded to increase the gain of an AC signal. The overall gain AV can be calculated by simply multiplying each gain together. That is AV equal to AV1 into AV2 into AV3 up to AVN. If the gain of each amplifier stage is expressed in decibels, the total gain will be the sum of the gain of individual stages. Here, given the voltage gain of first amplifier AV1 equal to 100, the voltage gain of second amplifier AV2 equal to 200, the voltage gain of third amplifier AV3 equal to 100. Therefore, voltage gain of the combined amplifier is AV equal to AV1 into AV2 into up to AVN, which is equal to, we get 2000000. Voltage gain in decibel is equal to AV dB 20 log of AV, which we will get 126 dB. Question number 3. The figure shows series RLC circuit. What is the resonant frequency of the circuit and impedance at a resonance? The answer is option C 1592 kHz and 10 ohm. Given L equal to 100 microhertz, C equal to 100 picofarad, R equal to 10 ohm. Therefore, resonant frequency equal to 1 by 2 pi root LC. Substitute the value of L and C, we get the resonant frequency as 1592 kHz. At a resonance, the net impedance is purely resistive. Therefore, the impedance of a resonance is 10 ohm. Question number 4. Operational amplifier circuit given below behaves as option A log converter. Answer. Logarithmic and exponential amplifier of op-amp uses negative feedback. B naught equal to minus eta Vt log Vi by I naught R. Note. Oscillators use positive feedback. Comparators use no feedback, that is, it operates in open loop mode. Question number 5. The current through the resistance R2 in the given circuit is, answer is option A 0.75 ampere from A to B. Applying KCL at node A, we get 15 minus VA by 10 ohm plus 7.5 volt minus VA by 10 ohm equal to VA by 10 ohm. After solving, we get VA equal to 7.5 volt. The current through 10 ohm resistor is I equal to V by R. Substitute the values of V and R, we get 0.75 ampere. The direction of current is from A to B. As the polarity of I is positive, we consider the direction of current is from A to B. Question number 6. In a JK flip-flop, output Qn equal to 1 and it does not change when a clock pulse is applied. What is the possible combination of inputs Jn, Kn in this condition? X denotes don't care. Answer is option B x, 0. This is the excitation table of JK flip-flop. Qn is the present state, Qn plus 1 is the next state. and j and k input. If qn and qn plus 1 equal to 0, 0, jk equal to 0x. If it is 0, 1, 1x, 1, 0, x1, 1, 1, x0. Consider the case to change the output from 0 to 1. The input combination is either j equal to 1 and k equal to 0 or j equal to 1 and k equal to 1. We can write these two conditions combinedly as j equal to 1 and k can have any value, that is don't care. Therefore, x comma 0 is the possible combination of input for output qn equal to 1. Question number 7. The output stage of an audio amplifier has impedance of 800 ohm. An output transformer is used to match its impedance to an 8 ohm speaker. The turns ratio of output transformer is, answer is option B, 10:1. Transformers are used for impedance matching application. Here given RL equal to 8 ohm, RS equal to 800 ohm. For the load to match with source resistance, RS equal to RL by N square. Therefore, N square equal to RL by RS. Substitute the value of RL and RS, we get N square equal to 1 by 100. From that, we can derive the turns ratio N equal to N2 by N1 equal to 1 by 10. We know the turns ratio is N1 by N2, which is equal to 10. Therefore, N1 is to N2 equal to 10 is to 1. Question number 8. What is the time period of oscillation of the following circuit? Option A, 1.38 millisecond is the correct answer. Given circuit is adjustable multivibrator using BJT. The total length of time of the multivibrator cycle for a symmetrical output waveform is F equal to 1 by T, which is equal to 1 by 1.38 RC. Therefore, time period equal to 1.38 RC. In the question, it is given that R equal to 1 kilo ohm, that is resistor connect with base, and C is 1 microfarad. Substitute the values of R and C in time period equation, that is 1.38 into 1 kilo ohm into 1 microfarad. We get time period equal to 1.38 millisecond. Question number 9. A constant phase delay filter is option D, Bessel filter. Bessel filter. It provides ideal phase characteristics with approximately linear phase response up to nearly cutoff frequency. Though it has a very linear phase response but a fairly gently skirt slope. It is a minimal phase shift filter even though its cutoff characteristics are not very sharp. Hence, it is known as a constant phase delay filter. Bessel filters are used where phase characteristics is important. It is well suited for pulse applications. Question number 10. Which of the following is not true for an ideal operational amplifier? That is option C, common mode gain is infinity. CMRR, that is common mode rejection ratio, is defined as a ratio of differential mode voltage gain AD and common mode voltage gain AC. CMRR equal to AD by AC, where AD is the differential gain and AC is the common mode gain. Ideally, the common mode gain of the op-amp should be 0. That is, it must give a 0 output for common input at both the inverting and non-inverting terminal. Therefore, AC equal to 0. If we substitute the value of AC equal to 0 in CMRR equation, we get CMRR equal to infinity. Note: input impedance of an op-amp should be infinity, output impedance is 0, voltage gain is infinity, bandwidth is infinity, common mode voltage gain is 0, slew rate infinity, that is output can change instantaneously. Question number 11. What is the output of the following circuit? Assume that the op-amp is powered from plus or minus 15 volt supply. Answer is option B, minus 9 volt. Due to virtual ground or virtual short circuit, VA equal to VB equal to 0. Look at the figure. Apply nodal analysis. VB minus 3 by 60. VB and V are equal. VB minus 3 by 60 plus VB minus 2 by 40 plus VB minus 1 by 20 plus VB minus V0 by 60 equal to 0. After solving, we will get V0 equal to minus 9 volt. Question number 12. A signal of maximum frequency of 10 kHz is sampled at an IQ rate at the time interval between two successive samples is option A, 50 microsecond is the correct answer. Nyquist sampling interval is defined as the maximum time that is between regularly spaced samples that with permit the signal waveform to be completely determined and is equal to reciprocal to twice of the highest frequency in the sampling signal. Given Fm equal to 10 kHz, therefore Nyquist rate Fs equal to 2 into Fm, which is 20 kHz. Nyquist interval Ts should be less than or equal to 1 by Fs. Ts should be less than or equal to 1 by 20 kHz. Therefore, Ts equal to 50 microsecond. Question number 13. In the following circuit, what is the voltage across 2 kilo ohm resistor? Answer is option C, 8 volt. The given circuit is a Wheatstone bridge and given resistance makes it balance. Wheatstone bridge makes no current in 10 kilo ohm resistor here under balanced condition. That is, condition for balanced bridge is R1 R3 equal to R2 R4. The given circuit we said that condition for balanced bridge R1 R3 equal to R2 R4. So the voltage across 2 kilo ohm resistor is given by voltage divider circuit. V equal to 12 into 2 by 1 plus 2. We get V equal to 8 volt. Question number 14. The 6-volt Zener diode shown in figure has 0 Zener resistance and a knee current of 5 milliampere. The minimum value of RL so that the voltage across it does not fall below 6 voltage is answer option B, 80 ohm. Consider the figure. Given Vz equal to 6 volt, Iz minimum equal to 5 milliampere. Since we require a constant 6 volt across R, Is equal to 10 minus 6 divided by 50 ohm, which is equal to 80 milliampere, which is the value of Is. IL maximum equal to Is minus Iz minimum. Substitute the values of Is and Iz minimum. That is 80 milliampere minus 5 milliampere, which is equal to 75 milliampere. Therefore, IL equal to Vz by R. From that, we can rearrange into R equal to Vz by IL. We know the value of IL equal to 75 milliampere and the value of Vz equal to 6. Substituting the values of Vz and IL, we get the value of R equal to 80 ohm. Question number 15. The characteristic or intrinsic impedance of free space is approximately option B, 377 ohm. Intrinsic impedance. Intrinsic impedance of a medium can be defined as the impedance which an electromagnetic wave faces while traveling in a medium, where eta equal to root of mu divided by root of epsilon. Also eta equal to E by H, where E is the electric field component and H is the magnetic field component. These two are the equations we generally use while solving the equations. For free space, mu equal to 4 pi into 10 raised to minus 7 Henry per meter and epsilon equal to 8.85 into 10 raised to 12 farad per meter. Substitute the values of mu and epsilon in eta, we get a value of 376.7, approximately 377 ohm. Question number 16. Which of the following statement about a common collector amplifier is true? That is unity voltage. Again, option C is correct. Common collector amplifier, also known as voltage follower or emitter follower. Collector terminal is common to both input and output. Voltage gain cannot exceed unity. Question number 17. An op-amp amplifier of gain 10 is used to amplify a sinusoidal signal with a peak amplitude of 0.5 voltage and a frequency of 25 kHz. What should be the minimum slew rate of the op-amp used? Option C, 0.785 volt per microsecond is the correct answer. We know that for a sinusoidal input, Vi of t equal to Am sin 2 pi fmt. Output is V0 of t equal to Av Am sin 2 pi fmt, where Av is the gain of op-amp. The rate of change of output dV0 divided by dt equal to Av Am 2 pi fm into cos 2 pi fmt. The maximum rate of change is slew rate, which is therefore slew rate equal to dV0 by dt of maximum, which is equal to, we know, maximum value of cos theta equal to 1. Substitute the value of 1, we get AV AM 2 pi FM. Given AV equal to 10, AM equal to 0.5 volt and FM equal to 25 kilohertz. Therefore, slew rate equal to 10 into 0.5 into 2 pi into 25 into 10 raised to 3. We get the slew rate equal to 0.785 volt per second. Question number 18. What is the role of rate of voltage gain versus frequency of a second order low pass filter? Answer is option B, minus 12 dB per octave. The frequency response of the second order low pass filter is identical to that of the first order type, that the stop band roll off will be twice the first order filters at 40 dB per decade or 12 dB per octave. This is the response of the second order filter. Question number 19. If the potential difference between 2 points in a circuit is V, the work done in moving a charge Q from lower potential to higher potential is, answer is option B, VQ. The amount of charge Q that flows between 2 points at potential difference V is QC. Thus, the amount of work W done in moving the charge W equal to VQ. The last question in this video is 20th question. That is, in an RL series circuit, when resistance and reactance are equal, what's the answer? From that is option C, current lag voltage by 45 degree. In RL series circuit consisting of inductor L, resistor R, it can be connected either in parallel or series. This is series circuit. Let the applied voltage be V0 equal to V0 sin omega t. Then the instantaneous current lag the voltage by an angle of phi. Then the instantaneous voltage and current is E equal to E0 sin omega t into I equal to I0 sin omega t minus phi. The phase angle is given by phi equal to tan inverse of XL by R, where XL is the inductive reactance and R is the resistance. Here given inductive reactance and resistance are equal, that is XL equal to R. Therefore, phi equal to tan inverse of 1. Therefore, value phi equal to 45 degree. Thank you.